Hello, class. This is Dr. Mu-tor Flood. Welcome to Statistics. This lecture is going to be on Chapter 1, an introduction to statistics. And let's get right into it. I'm going to share my screen. All right, let's share it. Give me 1 second. Okay. All right. So again, this is Chapter 1, Introduction to Statistics. And so in this particular chapter, what we're going to learn about is going to be some key statistical terms, some measurement terms as well, some basic research terms, some very preliminary things about statistics in science. And finally, we're going to discuss what is called summation notation, which is going to be a very key part of the formulas that you'll be using in this class. So statistics is going to require some basic math skills. Statistics isn't a math class, but it does require some math, all right? And so if you have inadequate math skills, it could put you at risk in this course. And so a way to avoid that, because all of y'all are high school graduates or at least have your GED, so you have come across the math that you'll need in order to be successful in this class. If you need a refresher, there is in your textbook, Appendix A Math Skills Assessment and Math Skills Review. And I suggest you go through those, make sure that you understand how to answer those particular kinds of questions. It's basically a review from the math that you learned from around first grade to algebra, so around first grade to ninth grade. The PowerPoint for the math skills assessment is in your module section, as well as all the other PowerPoints that you'll be utilizing each week of this course. So what do I mean when I use the term statistics? All right. So statistics actually means statistical procedures. However, people in regular language use statistics in many different ways, but it technically means statistical procedures or procedures to get statistics. All right. And so there are some uses of statistics, or in fact, there are many uses of statistics. One is that it's going to help us to organize and to summarize information. So when we have data or when we do studies, we're going to have a lot of information. And statistics is going to help us organize that information so that it is understandable and relatable to the people who are reading it and to the researchers themselves, and be able to summarize it. So somebody can get a quick look at your study or your data and kind of understand what's going on. And so basically they can determine exactly what conclusions are justified based on the results that were obtained. Now, the goals of statistical procedures is going to be to have accurate and meaningful interpretations of the information that you gleaned from your studies, and also to standardize evaluation procedures. So when I do certain kinds of statistical tests, we all statisticians, all people who use those statistics are in agreement on how we are going to utilize our data to and the formulas that are used in order to come up with those particular statistics. Furthermore, once we come up with those statistics, based off the statistics that we use, all statisticians and people involved will have a really good idea of why that particular statistics was used and how to interpret those statistical procedures and the information that you got from them. So one of the first and most important things to understand is the difference between what are called populations and what are called a sample. And so a population is going to be the set of all the individuals that the researchers are interested in a particular study. So they're going to vary in size, and a lot of times they're quite large. So if I say, hey, I'm interested in studying cotton-tailed bunnies, and so if I want the entire population of cotton-tailed bunnies, well, that could be thousands or millions of cotton-tailed bunny rabbits. So those can be quite large. Or sometimes populations could be very small. If I want to study, you know, if I want to try and create a treatment for people who have stage 4 colon cancer, well, that population may be a lot smaller. All right. But usually populations are quite large. So that's a population. All right. The next thing is what a sample is. So a sample is going to be a set of individuals or things or animals or objects that are going to be selected from their respective population. And the sample is going to be used or is intended to be used to represent the population that they came from. So let's go back to my example with the cotton-tailed bunny rabbits. Let's say there are 20 million cotton-tailed bunny rabbits. And I want to study something about those cotton-tailed bunny rabbits, right? The 20 million would be the population of cotton-tailed bunny rabbits. But in my study, I'm not going to use 20 million bunny rabbits in my study. So what I'll do is I'll take what's called a sample. I'll take a smaller subset of that population. So instead of having 20 million bunny rabbits in my study, I'll have 60 bunny rabbits in my study. All right, so it's a set of individuals that is selected from the population. All right. So what is the relationship between the population and a sample? Well, again, the population represents all the individuals of interest, every single individual in that particular population. All right. So as you see, these arrows are pointing to the next one would be that, hey, the sample is going to be selected from the population. All right. So if I use the cotton-tailed bunny rabbits of 20 million, I take 60 of those bunny rabbits, and that would be a sample. And now, following the arrows, the sample, right, are the individuals selected to participate in a research study. So let's say I'm trying to figure out the growth rate for bunny rabbits, right? So that is a research study that I'm taking that sample that I got from the population and using it in my study, all right? And so I'm going to carry out this particular study, right? Going to the next arrow, right? And once I carry out the study, I'm going to get some kind of results. And then what I want to do is I want to take the results that I got from my study using a sample, and I want to generalize the results to the larger population. So if I found some information, so for example, if I found some information about the growth rate of the bunny rabbits that I used in my research study, the sample, I want to say, hey, the growth rates will be the same in the population of the bunny rabbits. It's just not, uh, the information that I got is just not applicable to the study I did on those particular 60 bunny rabbits. It's applicable to all the bunny rabbits in the population. That's the idea. That's what I want to do. I want to be able to generalize, all right, my research results. All right, so now we're going to move on to some terms. All right, some of these you'll see very often in this class, others you won't see very often, but when you're reading studies, these terms will come up very often. All right, so the first one is a variable. All right, now a variable is going to come up a whole lot. All right, and a variable is a characteristic or condition that changes or has different values for different individuals. So a variable is, again, a characteristic or condition that changes. It has different values for different people, different individuals. So we could take a host of other variables, but let's stick with people. So people have what are called individual differences. Two people are almost never completely alike. All right. A variable could be hair color, right? Somebody has blonde hair, another person has red hair, another person has brown hair, another person has black hair. All right. So hair color would be the variable. It's a characteristic that changes or has different values for different people. All right. We could also give 10 people a test, an SAT test, let's say, and each of them are going to get a different score, right? That SAT test is a variable. All right. It's a variable. All right. Because it has values that can change for different individuals. All right. Another variable could be race. So you could be, Latina, you could be African American, could be white, you could be Pacific Islander. So that is a characteristic, right? That changes or different values. All right. When it comes to the term condition, right? Well, when we're doing a study, we'll talk about this a little bit later in this chapter, but you could have two groups of people that you're studying, and one group is going to get what is called the experimental treatment. Let's say we have a new drug. And so we're going to give them that drug in our study. And another group that we're going to use to compare to the group that we have given the drug to is not going to receive the drug. And so those two groups are in two different conditions. And so the variable in this case would be treatment, all right? Whether you are in a group that gets treatment or whether you're in a group that does not get treatment, all right? And those, again, it's a variable because that condition changes or has different values for the different individuals in those two particular groups. So the next term is what's called data, and that's a plural term. All right, data is plural, and it's the measurements or observations of a variable, right? So if I, have a class, right, and I take the whole class's measurements in relation to their height. So I measure their height, right? So let's say there's 30 people in the class, and I measure their height. All those height measurements would add up to what we would consider to be data. All right, it's a measurement or an observation of a singular variable. Then we have what's called a data set. So this is a collection of measurements or observations. All right. So if we took a couple of different variables and measure them for the class. Let's say we took a measurement for height and weight and eye color, right, for everyone in the class. Well, that would be a collection of measurements or observations, and that would be a data set. Then we have what is called a datum, and that is singular. We don't use this term very often because we don't usually get just one single measurement or observation. We usually get a collection, but the term is important. You may see it every now and again. So again, a datum is a single measurement or observation. So if I measure you and your height, the score that I get or the measurement that I get for your height is called a datum. All right. The term that we see most often instead of the term datum is, and what you'll see in your textbook almost exclusively, is going to be the term either score or raw score. All right. So when I take a measurement of a particular individual, that is going to be what I get is going to be their measurement score or their what's called a raw score. All right. So some more terminology to kind of get us all prepared for when we start discussing different kinds of studies and statistics used for those particular studies. So these two terms, one is what's called a parameter, right? And so what is a parameter? A parameter is going to be a value. It's usually a numerical value, right? It has some kind of numbers, some kind of quantity. And it's going to be something it's going to be a numerical value that's going to describe the population. All right. And so it comes from measurements of individuals in the population. So for example, let's say I have a population of 100. The population is 100 people, is made up of 100 people who have stage 4 colon cancer, right? If I take the height, if I measure the height of all 100 people, all 100 people in that population, the total population, and then I get what's the average height. So I add up all the heights of all the 100 people and divide by 100 to get the average. The average height for the population would be a parameter because it's going to be a numerical value that's going to describe the population. All right. And so how I got that is I measured everyone in the population. So a good way to understand this, because we're going to use the term parameters and populations a lot in this class, is that they both start with the word P. So if we're dealing with a population, right, any kind of numerical value like a mean or the mode, or the range, or any number of other statistical terms describing the entire population using that numerical value is going to be a parameter, population parameter. However, we normally don't use or don't have the information to get a parameter. That's usually mostly because populations are extremely large. So we're not able to measure everybody on this one key aspect or one key variable in the population because it's usually impossible. So we'll move on to the next term, which would be we do instead what's called a statistic. All right. And so a statistic in this case, right? I know I said earlier that a statistic is a statistical procedure, but in this case, a statistic is a value, usually a numerical value that's going to describe a sample. Remember, a sample is a subset, a smaller portion that is taken from the larger population it came from. So the statistic is going to be derived from measurements of the individuals in the sample. So if I were again to have those bunny rabbits right? I have a sample of 100 bunny rabbits, and I take the weight for all of the bunny rabbits, the sample of bunny rabbits in my study. And if I add up all those weight sizes and divide by how many bunnies I have, I would get an average, or what's called the arithmetic mean. And that mean that describes, it's a numerical value that describes a sample, right? That would be what we would consider to be a statistic. Again, a numerical value that describes a sample. And a good way to understand this is that if we're dealing with samples and we get some kind of numerical value that's describing the sample, it's going to be called a statistic. So sample statistic, whereas dealing with a population and we get a numerical value that describes a population, it's going to be called a parameter. So population parameter, sample statistic. All right. Okay. So moving on. So there are two different types of statistics, right? There is descriptive statistics, and there are what's called inferential statistics. A little bit early on, I kind of discussed the inferential statistics, but I'm going to start with descriptive. So descriptive statistics is going to allow us, once we do some kind of study or get some kind of data, descriptive statistics is going to allow us to, again, summarize this particular data to make it readable. We're going to be able to organize it, and we're going to be able to simplify it. We're taking data and making it make sense to us and anybody who may come across our research or our studies. And we would do that by utilizing descriptive statistics. And so some examples of the way we summarize and organize or simplify data is that we would put the data in a table, which we'll talk about next in the next chapter, or we'll put it in a graph. Graphs are a great way to simplify data and organize it in a way that makes it understandable by you, the researcher, and anybody who, again, looks at your research. All right, so that's descriptive statistics. And descriptive statistics are fairly easy to do. A lot of descriptive statistics are things that you know about already because you've come across them in grade school. Things such as the mean, the median, the mode, bar graphs, things of that nature. This class is going to focus, the later half of the class especially, is going to focus more on what's called inferential statistics. And the root word of inferential is inference, to infer, essentially to assume, all right, based off of good information. So we're not just taking wild guesses, right, which is what an assumption would be, but we're taking more scientifically evaluated guesses. All right, so inferential statistics, we're going to study samples, right, because sample statistics, right, we're going to study samples, and we're going to use the information that we get to make generalizations about the population that the sample came from. And we're also, usually we do this by interpreting experimental data. So we do some kind of study and we get some kind of results utilizing our sample and doing some kind of statistic. And we're going to take those statistics that we received from our study about our sample, and then we're going to generalize it to the larger population that our sample came from. And so some terminology that you may come across with this is margin of error and what is called statistically significant, which is going to be that last term. Statistically significant is going to be a very key term in a lot of the statistics that we utilize in this course. All right, so one key thing that we need to understand is that when we're sampling, we're always going to get what is called sampling error. All right, and what exactly is sampling error? All right. So sampling error doesn't mean you made a mistake as a researcher. All right. It doesn't mean you messed up. What sampling error means is that a sample is never identical to the population it came from. Right. So for example, if I if I were to have measured all 20 million of the bunny rabbits in my example and measured the height of the bunny rabbits, right? I would get an average height, right? Now, if I just took 20 of those bunny rabbits and measured their height, right? Again, a sample, I could get an average height as well. But the average height using the 20 bunny rabbits is not going to be the same as the average height using all the bunny rabbits in the total population. That difference between those two measurements is what is called the sampling error. It's the discrepancy or the amount of error that exists between a sample statistic and the corresponding population parameter. In case of my example, the average height for the population of bunny rabbits is a population parameter. The average height for the 20 bunny rabbits in my study is what is called a sample statistic. And those two, again, those two numbers are not going to be the same. And the discrepancy of the difference between those two is what is called the sampling error. All right. So to make a more concrete example using human participants, all right, is let's say I'm using the population of, so the total amount of college students at a particular college, right? Let's say there are 1,000 of them. And so I measured all 1,000 of the students in that particular school on 3 variables. One was their age, one was their IQ, and one was if they are male or female, right? Those are all variables because they all take on characteristics or conditions that can change for each individual. All right, so here are the population parameters for average age is 21.3 years. For average IQ is about 112.5. And the percentage breakdown of gender at the school is 65% female to 35% male. And let's say I took 2 samples from the population, right? So remember, the sample is going to be a smaller subset taken from the larger population. So each sample has five people, all right? And so I'm going to measure those 5 people on those same variables as I measured the entire population, that being age, IQ, and gender breakdown, right? And so what I would be getting for those would be what's called sample statistics. Again, it's a quantitative value that's describing a sample. And so if we look for sample number 1, the average age that I got by measuring all 5 people, all right, in the first sample is 19.8, right? 19.8 is different than the average age of all the people in the population, which was 21.3. The difference between 21.3 and 19.8, that is the sampling error for the variable age between the population parameter of age and the sample statistic of age. I could also look at the difference between the average IQ score for the population parameter and the sample statistic. For sample 1, the average IQ score is 104.6. But when I measured the entire population and got an average IQ population parameter, it is 112.5. Again, that difference between the two is what is called the sampling error. Not only are samples going to be different from the populations it came from, but they're also going to be different from other samples that we've taken from the same population. So if we look at sample 1 in comparison to sample 2, well, the average age in sample 1 is 19.8, and in sample 2, the average age using 5 new people, or 5 different people from sample 1, is going to be 20.4, right? So those are going to be different as well. And these natural differences exist by chance, right? And again, is called sampling error. So a kind of a breakdown of experimental research. So as you can see, in step 1, we have we set up some kind of experiment, right? Let's say we're comparing 2 different study methods. One method is where people are going to be reading from printed pages to study, and the other one is another sample is going to be people in my sample are going to read from a computer screen, right? Those 2 samples came from the population of college students. And so I'm going to get data by having each of the people in each of the samples that I have, but either read from the printed pages or read from the computer screen. And then I'm going to score them on some kind of variable. So this variable would be the test scores. And so now I have some numerical values, right? And what you would do in a study, the next part, which in this case was called step 2, is I would get some descriptive statistics to help me organize and summarize the data and simplify it. So I could get what the average score was for the 2 different samples, and I could make some kind of graph, which in this case, which we'll talk about in the next chapter in more detail, is called a modified block histogram, right? But these are just ways for us to simplify the data and to organize and summarize it so that we could make better sense of it. Lastly, so that would be an example of descriptive statistics. And then lastly, in step 3, I could do some kind of inferential statistics, right? So I could say, hey, the sample data show that there is a 4-point difference between the 2 methods of studying, right? So the average score for those who read from printed pages is 26. The average score from those who read from a computer screen is 22, right? So the score is a 4-point difference between these 2 scores. However, there are 2 ways to interpret the results, right? The first way to interpret it is that, hey, there actually is no difference between the 2 study methods, and the sample difference is due entirely by chance, a basically sampling error, right? There's no difference between the 2 study methods. This is just sampling error, the natural discrepancy between samples and the natural discrepancy between the sample and the population. The second interpretation of the results is going to be that there really is some kind of difference between the 2 methods, right? And the sample data accurately reflect this particular difference. So in this case, we would say something like, oh, the sample who read from printed pages have higher scores than those who read from a computer screen. And so reading from printed pages is going to yield higher scores than reading from a computer screen. That's what the second interpretation is about, right? And that's what's called an inferential statistic, where we're inferring, right? We want to generalize to the larger population of college students, basically saying, hey, well, which one of these 2 things are better? Should you study using reading from printed pages, or should you study by reading from a computer screen? All right. And then we're going to interpret those results and relay those back to the people who read our study. All right, so some questions. All right, so it's a learning check. I'm going to do these throughout the semester. So a researcher is interested in the effect of the amount of sleep on high school students' exam scores. A group of 75 high school boys agree to participate in the study. The boys are a statistic, B, a variable, C, a parameter, or D, a sample. All right. So it says that, hey, a group of 75 high school boys agree to participate in the study. It doesn't say that these are all of the boys in the high school. So if it's not all the boys, then that means it's a smaller subset, a smaller portion of the larger population of high school boys. So that would make this a sample. All right, so this is a sample. All right, so here's another learning check. All right, so we're going to decide if this is true or false, right? The first one, most research studies use data from samples. Is that true or false? Well, that is going to be true, right? Like I said earlier, populations are very, very large. We normally don't study populations directly because they're too big and it's too time and too costly and too labor intensive to study an entire population. So instead, we take samples and study the samples and then infer, inferential statistics, infer things about the population that the sample came from. So most research studies are going to use samples. All right. All right. Let's continue. All right. So like I said earlier, variables are characteristics or conditions that change or have different values for different individuals. All right. The evaluating those differences or changes in variables, when we're doing that, we must be able to define and measure the variables being studied. All right. So we're going to talk more about this kind of measurement that we're doing. So variables and measurement. So scores are obtained by observing and measuring variables that scientists use to help define and explain external behaviors. Right. So if I wanted to explain intelligence or health or IQ or different methods of studying, right? All right, we're going to measure some kind of variable and use it to help us define and explain some kind of external behavior. So the process of measurement is going to consist of applying carefully defined measurement procedures for each variable. The way we do that is largely through what are called constructs and operational definitions. So what is a construct? Right? We hear this in the media a lot. Oh, this and this is a construct, or we'll hear a lot of times social constructs, right? So a construct is going to be an internal attribute or characteristic that cannot be directly observed. And so it is useful for describing and explaining behavior. Humans are very complex, so not everything that we have words or understand is something that could be directly observed or measured. So let's talk about an example. IQ or intelligence. We can't directly observe intelligence. Intelligence is a construct, all right? It's some kind of internal attribute or characteristic, all right? But we all kind of have an idea of what intelligence is, all right? Um, uh, so that is an example of a construct. So let's take another construct, something that is more, a little bit more concrete. Let's talk about hunger, all right? We can't directly observe hunger, all right? We know what hunger is, but we can't directly measure it or observe it, all right? It's something that we kind of projected to the world, right? It's not something that exists concretely, something that indirectly we understand when we say the term hunger, what that means. And so hunger is a construct. So what do we do? All right, a lot of social science, and most of y'all are either in psychology majors or criminal justice majors or nursing, right? There's lots of different constructs that we have in our society that we deal with on a regular basis. We got to understand what it means. And so we have to be able to have a way of studying those constructs, right? So if I say a happiness, right? Happiness is a construct. All right, what does that mean? Well, we kind of know what happiness means, right? So how do we study things that are constructs? Well, what we do is we get what's called an operational definition, all right, for these particular constructs. And what is an operational definition? All right, an operational definition is going to identify the set of operations required to measure an external, in this case, observable behavior. And it's going to use those resulting measurements as both a definition of the construct and a measurement for this particular construct. Excuse me. So let me give you an example. So let's go back to hunger, right? We can't directly measure or observe hunger because it's an internal attribute or characteristic, right? But we all kind of know what hunger means, right? So one way that researchers could operationally define hunger is by saying, hey, if you haven't eaten in 12 hours, then you will experience what is considered to be hunger. Or so that's one way we could operationally define hunger, right? And then we could use that as a measurement in order to carry out different kinds of studies. Another way to measure using an operational definition, the construct of hunger would be, we could say, hey, if your stomach grumbles, a certain amount of times in a 30-minute period, then you are experiencing hunger, right? So now we've taken something that's a hypothetical construct and we've given a way to measure it. And the way we measure it is also being used to define the construct. So now the definition of hunger is somebody who hasn't eaten for 12 hours or more. Or hunger is operationally defined as someone whose stomach grumbles X amount of times in a 30-minute period. All right. So that would be an example of the construct and then getting a operational definition for the construct. Let's talk about another example. Let's talk about happiness, right? Happiness is an internal attribute or characteristic that can't be directly observed. You can't observe a happiness, all right? You can't measure directly happiness, all right? But humans are crafty. We could measure happiness indirectly. So what we can do is we can say, hey, happiness is you smiling X amount of times in a certain period of time, all right? Or a happiness is we've created this assessment, this test that measures happiness. And if you score high on this test, then we will say that you are happy, all right? Now, the assessment or the measurement tool that we're using, all right, It measures happiness, and it provides a definition for the construct of happiness. We'll say, hey, this person scored very highly on this happiness test, so they are happy. All right. So they are happy. We do the same thing for our Q test, same kind of logic. All right. And we do that for a multiplicity, a myriad of things in nature that we can't directly observe. So we indirectly observe it and measure it through behaviors that are related to what we believe the construct is about. All right, so that's hypothetical, that's constructs and operational definitions. All right, so let's go back to these variables, because there's different kinds of variables. And this is very important for the different kinds of studies that we'll look at and statistics that we'll conduct for this particular course. So we have discrete and continuous variables. All right, so first, a discrete variable is going to have separate indivisible categories. All right, so you can't cross into these categories. They don't mix. They are discrete. They are separate. You can't divide the categories into smaller chunks of the particular category it is. The category is what it is, and it's separate from other categories. So no values can exist between the two neighboring groups. So let's say if I have the variable of eye color, all right? So I have brown eyes, green eyes, and blue eyes, right? Those are separate categories, right? Either you have blue eyes, or you have green eyes, or you have brown eyes. You don't have both, all right? And there's no middle value between those eye colors, all right? You have one or the other, all right? That's a discrete variable. Another one is, let's say I have a test that I created that measures personality. And there are three types of personalities. There is personality A, personality B, and personality C. I give people the test. People can't be, you could only have one of those personalities, A, B, or C. You can't have A and C, or A and B, or the middle of A and B, or the middle of B and C, or the middle of A and C, et cetera, et cetera. All right. These are separate categories. They're indivisible. Can't divide into them. All right. And there's no values that exist between the categories. They're separate. All right. So that's a discrete variable. All right. I'm going to give you more examples of these because it's a very important point that you need to be comfortable with in this course. The next is what's called a continuous variable. All right. And a continuous variable has an infinite number of possible values between any two observed values. All right. In this one, every interval is divisible into an infinite number of fractional parts. All right. So let's give some more examples to these so that it can make more sense. All right. So discrete variable. All right. So for examples of this is the number of children in a family, right? So either you have one child in the family or two children or three children or four. You can't have 2.3 children. It's not possible. You may hear this stated a lot when they talk about demographics of families in the United States or the world. But if you think about it logically, you can't have 2.3 children. You can't have 3.9 children. You either have a child, one whole child, or you have or you have another child. It goes up by, in this case, ones. Can't have somewhere between 1 and 2 children. Doesn't work that way. Another example would be the Friday night attendance at a cinema. All right. You have people who go to the cinema. You can't have 50.1 people who go to the cinema, right? What is the 0.1? Is that somebody's hand? It doesn't make sense. You could have 50 people who attended the cinema. You could have 49 people who attended the cinema, but you can't have 50.5 or 49.7 or 23.23. Those aren't that doesn't make sense. All right. Another example would be the number of patients a doctor sees in one day. Right. The doctor doesn't see 25.7 patients. He sees 25 patients. He sees 26 patients. Right. So they're separate, indivisible categories. Right. Now let's talk about the continuous. I didn't give you an example in the previous slide. Right. But a continuous variable, again, has infinite number of possible values between any two observed values. All right. And the intervals, a real interval is going to be a set of real numbers that contain all real numbers lying between any two numbers of the set. All right. So that's kind of wordy, right? But for example, the set of numbers between 0 and 1, all right, is infinite, right? Is infinite. So the numbers between 0 and 1 are infinite. I could have 0.0. I could have 0.01. I could have 0.00012. I could have 0.9. I could have 0.913. I could have 0.9145. And this could go on for infinity. I have an infinite amount of numbers between 0 and 1. All right. And so all those numbers also can be divided into fractional parts, right? So an example of kind of a continuous variable is height, right? I can measure height in feet, in centimeters, in inches, in yards, right? And between 1 inch and another inch, there's an infinite number of other possible values. So height would be a continuous variable, all right? Weight, for the same reasons as height, would be a continuous variable. The depth at which a drilling team strikes oil, like how far into the ground did they go? Well, they could have went 27 meters or kilometers. But between each of those kilometers, there's an infinite number of other possible values. All right. Another example is the volume of milk produced by a cow. All right. Volume itself is the volume in liters, right? We could go into milliliters, all kinds of different values between 1 liter and another liter. All right. So those are the difference between continuous variables and a discrete variable. All right. So that's going to bring us to scales of measurement. This is going to be important because when we're deciding what statistics to use based off the variables that we have and the questions that we're asking, we're going to need to know what scale of measurement those variables are. All right. And so scales of measurement is a measurement assigns individuals or events to categories. The categories could be names, such as male or female, or employed or unemployed, right? Or they could be numerical values, such as 68 inches, right? Or 175 pounds, right? So the complete set of those categories is going to make up what's called a scale of measurement. Now, those relationships between the categories determine the different kinds of scales. All right, and so we have 4 scales, and we're going to talk about those scales. All right. So the first scale, and the scales are going as we read, they're going from simple to more complex. All right. So the first scale of measurement is called a nominal scale of measurement. And nominal just means in name only. So the characteristics of these kind of scales of measurement, of this scale of measurement, is that it's just a label, just a category. All right. There's no quantitative distinctions between the different categories. So some examples. Gender is a nominal category. You're male or you are female, right? There's no quantitative distinction, no numerical distinction between that, right? You're not 75% male, 25% female, right? It doesn't work that way. You're either one or the other, right? In these kind of categories. You have one label and only that label. You're in that one category and only that category, all right? Another example would be diagnosis. Either you have the disease or you do not have the disease. There's no in between with that. There's no, oh, I sort of kind of have the disease. There's no, either you do or you do not. All right. One very important nominal example that we're going to use very often in this class is if you are in the experimental group or you are in a control group, right? In the experimental group, those of you who are in my research methods class, are the people who are going to get the experiment or the treatment or the drug. The control group are people who are not going to get anything. They're not going to get the experiment or the treatment or the drug, right? When we put somebody into one of those groups, right, those are just categories. They're labels. You are in the experimental group or you are in the control group, all right? So that would be a nominal variable. Some other examples of this would be a political party, right? Either you are a Democrat or a Republican or an independent, right? But you're not a Democrat and a Republican. You're not an independent and a Democrat, right? You are either in a category labeled with that category, or you are not in that category. And there's no quantitative distinction between the political parties. You're not, one is not greater or lesser than the other in a numerical sense, right? As far as political parties are concerned. We could also have another example of a nominal would be blood type, right? There's about 5 or 6 different blood types. There's A, B, AB, and O. And then there's either positive or negative values for each of those respective blood types. You can't have AB blood and O blood. Doesn't work like that, all right? In fact, for my pre-nursing students, right, if you mix these bloods in the wrong way, right, in doing blood transfusions, you can kill the person, right? So it's very important that these categories do not mix with each other, right? Certain categories. So the blood type is just a category. Race is just a category. It's a category, it's a label, all right? All right. Another one would be the zip code you live in, right? The zip code, it brings something more interesting to this because it has numbers in it, but those numbers don't really they have a meaning, but not in the way that we're using the numbers. If I say, hey, I'm putting all the people who live in the zip code 32120 in a group, and those who have a zip code that they live in of 32124, well, I just made two categories based off of zip codes. The zip code number is essentially irrelevant. What's important is that we made categories, all right? And we label those categories based off the differences in zip codes, all right? So that would be examples of a nominal scale of measurement, all right? Now going up in complexity, we have what are called ordinal variables. And the word ordinal essentially means rank, all right? And so in ordinal variables, all right, we have what we have in a nominal variable or nominal scale of measure. We have categories, right? Categories of observations. However, with an ordinal variable, we can categorize things by the size or their magnitude, essentially ranking them from least to most, from a little to a lot, and the other way around, and vice versa. So for example, the rank in a class, either you're first in your class or second or third or 300th in your class, right? But we know that the person who ranks number one in class is higher than the person who ranks number two in class. And we know that number two ranks higher than the person who is the third in their class, all right? So we can organize it by size or magnitude. Now, what we can't do with an ordinal scale of measurement, we know that, let's take the rank in class. We know that the person who is number one in class is ranked higher than the person who's ranked number two, but we don't know by how much. We don't know if the difference between those two is very, very small or extremely large. We don't have that kind of information, but we can organize and rank the data that we have by size or magnitude. Other examples that are similar to this, that are also ordinal variables, are clothing sizes. You can be small, or you can be, it's not even small, then extra small, small, medium large, extra large, extra extra large, extra 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 large, right? Those are categories, and we can organize them by size or magnitude, right? We know that medium is bigger than small, extra large is bigger than large, right? The thing is that if we just have that information, right? If we just have small, medium, large, extra large, we don't know how much bigger medium is in comparison to small, right? We don't know how much smaller large is in comparison to extra large. All we know is that one is bigger and smaller than the other, all right? Just like the ranks in class, another example would be Olympic medals. All right, somebody received the gold medal, so they did the best. Somebody received the silver medal, which is essentially second best. And somebody received the bronze medal, which is the third best. We don't, with just that information, let's say we don't have any other time or anything like that. We just have who won what medal. We don't know how much better the person who won the gold medal did in comparison to the one who won the silver medal. All right. All we know is that gold did better than silver and silver did worse than gold. All right. So we know kind of the magnitude. All right. We know those kind of differences. Other kinds of ordinal examples is going to be socioeconomic status, right? So SES. So we could set those in the categories such as you're in lower class, you're in middle class, you're upper class. We know that the lower class has less money than the upper class. We just don't know how much, by how much. Another example would be educational level, right? We can rank that. right? You associate's level, associate's degree, bachelor's, master's, uh, doctorate, right? We know each of those have more education than the other, all right? And we can rank them. We just don't know how much of a difference they have. All right. So going up in complexity, right? We have what is called an interval scale of measurement. And the interval scale is going to have what the ordinal has, but just a little bit more. So it has ordered categories, just like the ordinal scale did. But what this has is the intervals. What makes it different is that the intervals between categories are of equal size. All right. The third kind of important point to note about interval is that they have an arbitrary or an absent 0 point. All right. So wherever the 0 lies is usually just arbitrary. So some examples of this is temperature. Now, temperature in a very specific way. So the example is that I'll give you is temperature in Fahrenheit or Celsius, right? If the temperature in Fahrenheit is 70 degrees and somewhere else has a temperature of 60 degrees, right? We know that the difference in temperature between those two temperatures is 10 degrees. 70 degrees in one place and 60 degrees in one place, there's a difference of 10 degrees, right? That 10-degree difference is an interval. The intervals are of equal size, right? So we know that the difference between 50 degrees and 40 degrees is also 10 degrees. The difference in degrees between 110 Fahrenheit and 100 is also 10 degrees. All right. So again, those intervals between categories are going to be of equal size. However, when we're using either the Celsius or the Fahrenheit to measure temperature, we're going to have what's called an arbitrary or absent 0. So when I say when I mean arbitrary, I mean it doesn't have a true 0. A true 0 means that there is an absence of the thing that's being measured. So if I'm measuring on a Fahrenheit scale and I reach 0, right? 0 doesn't mean I no longer have any temperature to measure, right? Because we can go to negative numbers. It could be negative 10 degrees Fahrenheit, negative 20 degrees Fahrenheit, negative 33 degrees Fahrenheit, and the same with Celsius. So wherever the 0 is on those temperature scales, it doesn't mean that there is an absence. Wherever the 0 is, doesn't mean that there's an absence of the thing that is being measured. It just means that that's where the 0 point was placed, usually arbitrarily. All right. So another example of an interval scale is going to be what's called IQ, right? You get an IQ score, right? The IQ score doesn't have a 0 point. You can't score a 0 on an IQ test. I believe they give you like 200 points just for spelling your name correctly. So you can't get a 0. There's no 0. But we know that in an IQ test, if I score 110 and you score 100, well, that's a 10-point difference. I'm scoring 10 points better than you, and you're scoring 10 points worse than me, right? We can make those distinctions in an interval scale of measurement, all right? And we know that the difference, that 10-point difference is the same for any other differences of 10 points, right? In the IQ score measurement. So the difference between somebody who scored a 60 on an IQ test and somebody who scored a 50 on an IQ test is 10 points, the same as it was with 110 and 100. All right. Another example of an interval scale of measurement is golf scores, right? You can score above and below par, right? Essentially above and below zero, right? So it has the same kind of ordered categories. It lacks a 0 point because what we're trying to do is measure essentially, how many strokes you took in order to get the ball in the hole in golf. All right. So we have an arbitrary kind of 0 point in golf. Some other examples of interval scales of measurement is the SAT score, right? Or your credit score, right? You can't have you can't have a 0 credit score, and so the credit score is an interval scale of measurement. All right. Then now going up from complexity, we have what is called the ratio scale of measurement. All right, so this has everything that intervals have, the interval scale of measurement has, right? But also, what makes us different is that there's no negative values in a ratio scale of measurement. There also it's called an absolute 0 point, right? So when you have a 0 as a score on that particular measurement, you have an absence of the thing that's being measured. You no longer have it. It's not there anymore. And a ratio scale, you're able to make what are called ratios. All right. So some examples of this. If I give you a quiz, right, the number of correct answers, right, is going to be on a ratio scale, right? It has intervals between categories of equal size. It has a true 0 point, and there's no negative values, right? If you get a 0, that means you are absent of the thing that's being measured. In this case, your knowledge of whatever the quiz was on. All right. So a quiz would be an example of a ratio scale of measurement. Another example of this is the time to complete a task, right? There's a 0 point to this, right? If you could get you could not complete the task, which would mean is you get a 0, right? There's no negative values. There's no negative time you can get, right? Another example of a ratio scale is the gain in height, right? Since last year, you can gain 0 in height, right? You can't go backwards in height. It's not Benjamin Button, right? You're not getting smaller, all right? And so a really important part of the ratio scale of measurement is the ability to make ratios. So what is a ratio, right? A ratio is going to indicate how many times one number contains another. For example, the ratio of men's jobs to women's is 8-1. So that means every 8 male jobs, right, there is 1 woman job. All right. And so we could use that ratio. And so for every 16 jobs for men, there's going to be 2 jobs for women, right? And those are ratios. All right. So again, a ratio scale, on the other hand, is characterized by a 0 point that is not in an arbitrary location. Instead, the value 0 on a ratio scale is a meaningful point representing none or the complete absence of the variable being measured. The existence of an absolute non-arbitrary 0 point means that we can measure the absolute amount of the variable. That is, we can measure the distance from 0. This makes it possible to compare measurements in terms of ratios. So for example, an individual who requires 10 seconds to solve a problem, 10 more than 0, has taken twice as much time as an individual who finishes in only 5 seconds, which is 5 more than 0. With a ratio scale, we can measure the direction and the magnitude of the difference between measurements and describe differences in terms of ratios. So ratio scales are quite common and include physical measures such as height and weight, as well as variables such as reaction time or numbers of errors, again, like I said earlier, on a test. All right. Some other key things about the differences between these scales of measurement is that different ones do different things, obviously, right? So if we wanted to have, if there's an order of the values, right? I can't order the categories of race, right? Being white is not better than being black, right? It's not higher than being black, and black is not lower than white, right? Or eye color. If green eye color in comparison to brown eye color, there's no order to those categories. They're just categories, right? So nominal doesn't order things, right? Which we knew from our definition of it. But an ordinal scale of measurement does order values as well as interval and ratio, all right? However, if I wanted to make what are called counts or the frequency of things or people or participants in that particular category, well, I can do that with all 4, right? If I have 5 people in the category of who have green eyes, well, that's a count or frequency of 5. I can do the same in ordinal data, in interval and ratio data. If I wanted to calculate the mode, right? Remember, mode means the most, right? Well, I can do that for all 4 of these categories, right? What I can do for nominal is I can't calculate a median. Remember, the median means the middle number. There's no middle between categories on a nominal scale, right? There's no middle eye color. Either you have brown eyes or blue eyes, right? So I can't calculate a median, a middle, there's no quantitative value to make that particular to get a median value. But I can do that with ordinal. I can do that with interval. I can do that with ratio. If I wanted to calculate the mean, I can't do that with a nominal and ordinal variable, but I can do it with an interval and a ratio scale. All right. And lastly, I'm skipping ahead a little bit. The ratio has a true 0, meaning that when something is measured and they get a 0 on a ratio scale of measurement, that means that they have an absence of the thing being measured. All right. And there are 2 videos on these scales of measurement. I highly recommend watching these videos. I'm not going to play it for you here in the interest of time, but they're very helpful. All right, so some questions. Learning check 2, all right? So a study assesses the optimal size, right? The number of other members for study groups. The variable size of the group is what? Right? Well, the size of the group is going to be, well, first, could you have 0 people in the group? Sure, that would be an absence of the thing that's being measured. So that makes it a ratio scale, right? All right. Could you have, in the size of the group, right? Could you have 2.5 people? No, you can't. Either you have one person in the group or two or three or four. Well, so then that makes it also discrete, right? It's discrete and ratio, right? So that would be a discrete and ratio for the variable size of the group. All right. So the next question, decide if each of the following statements are true or false. So variables that cannot be measured directly cannot be studied scientifically, right? Well, that's false, right? Because we talked about constructs and hypothetical constructs and operational definitions, right? We do this all the time, specifically and especially in the social sciences such as psychology, sociology, anthropology, etc. All right, so we can measure constructs. So the answer is false, right? Um, Constructs, internal states can only be observed indirectly, but it can be operationally defined. For the second question, research measurements are made using specific procedures that define constructs. Well, that's going to be true. Operational definitions, we use those to help us make consistent measurements and provide construct definitions. And here are the answers to that. All right, so now we're going to talk about three different kinds of structures and research methods and their accompanying statistics. All right, I'm going to briefly go through this because we're going to go through this in a lot more depth when we start actually carrying out studies, all right, or statistics. All right, so data structure one is a descriptive research. And this is, for those of you who are in my research methods class, this is sort of a brief overview. And again, any of those who are in this class currently who may not have been in my class previously have had to have gone through research methods in order to be in this class. And so this should be a refresher for you as well. So data structure one, descriptive research, all right? If we use this kind of individual variables, right? You have one or more variables measured per individual, all right? So statistics describe the observed variable, and you could use category and or numerical values. So we could measure the height of that particular, of a group of people, right? And that would be a sample statistic, right? Or the average rainfall in the Sahara Desert. That it would be descriptive research. We're not, we're just measuring something and just giving you the information about it, right? We're not making any inferences. We're not generalizing. We're not comparing groups. We're not doing anything. We're just measuring it, and that's that. So in this example, right, if you look at the bottom, the weekly number of student fast food meals, right? So we have 9 people, in our study, and we looked at 3 different kinds of variables. One is the weekly number of student fast food meals, and we found out how many each person in our study had fast food meals in that week. The number of hours that they slept each day, that's going to be, a part of our descriptive research, right? And again, all we did was, we didn't alter anything, we didn't change anything, we just kind of described what was occurring in its natural state for each of these variables. And that's going to be descriptive research. We're just describing, all right? All right, so that was just descriptive research, but now we have relationships between variables, all right? So when it comes to relationships between variables, we can have 2 or more variables are going to be observed and measured. So there's one or two possible data structures used to determine what type of relationship exists between those two variables that have been observed and measured. The first one would be what's called the correlational method. We're going to learn how to do a correlation in a number of weeks from now. So in this one, we have one group of participants, and we're going to measure two variables for each participant. So let's say I measure, I get 10 people in my study. I get a sample of 10 people, and I'm going to measure each person in my sample on two variables, the variables being height and weight. And so the goal is going to be to describe the type and magnitude of the relationship between those two variables. What we want to know with the correlational method is if there's any pattern between those two variables, right? And essentially, this is considered a sort of a non-experimental method of study, all right? And so in this example, we have a student, right? We have 9 students, and we have two variables that we measured each student on, right? One is Facebook, time on Facebook, and the other one is academic performance. And so what we want to see in this correlational study is if there's a relationship between time spent on Facebook and academic performance. All right. And we're going to evaluate the relationship between those two variables. So notice that we have one group, and we're measuring each person in that one group on two variables. All right. So there's some limitations to the correlational method, right? The most important one is that correlation doesn't provide an explanation for the relationship. So, you know, the correlation does not imply causation. All right. This is one of the more important things that you need to understand. We can't get a cause and effect using the correlational method. We don't know what caused what. All right. And so there's a lot of very nonsensical correlations that exist. And they exist because a third variable usually is the one that is making the relationship between the two variables more apparent. So one example is drownings rise when ice cream sales rise. So there's a correlation between those two things, right? Drownings is a variable and ice cream sales is another variable. Well, obviously, drownings don't cause ice cream sales to go up, nor does ice cream sales cause people to drown, right? And again, we can't get that from a correlation. What is causing those two to seem to have some kind of relationship is that is temperature, right? In the summertime, temperature is hotter, so more people are, at pools or at the beach, and so inevitably more people unfortunately drown. Now, also temperature, when temperature increases, well, the ice cream people tend to consume more ice cream. All right. And so both of those go up as the temperature goes up. All right. And so these are some other kinds of funny and weird correlations, right? Again, correlation does not imply causation. All right. All right. So there's a third data structure if we're comparing two or more groups of scores. All right. So in this one, the setup for this one is that one variable is going to define the groups, right? And the second part of it is the scores are measured on a second variable. Excuse me. The third part of this is that both experimental and non-experimental studies use this particular kind of structure. So let's see an example, right? So in this one variable is the type of video game. So we set up a study where we have two groups. One group of children is going to get a violent video game. Another group of children are going to get a non-violent video game. All right. So the one variable, video games, is going to define the two groups. All right. And then the second variable is something that we are going to measure to get scores for each group. So the second variable in this case is aggressive behavior. So we're going to let the children play either violent video games in one group or non-violent video games in the other group. And we're going to see just how aggressive each group is, each of the boys or the children in each of the groups are. All right. And then we're going to compare. We're going to compare the two groups to each other and see, hey, is our children more violent when they play violent video games, or are they less violent when they play violent video games? So we're going to compare the two groups. So let's talk about this experimental method. All right. So the goal of an experimental method is, in this case, is to demonstrate a cause and effect relationship, unlike the correlational method. All right. And some hallmarks of an experimental method is that they have what's called manipulation. So the level of one variable is determined by the experimenter. All right. In the case of this particular, the previous example, the previous slide, right, we manipulated what group the children are going to be placed in. Either we are going to expose them to violent video games, or we're going to expose the children to non-violent video games. We, as the researchers, did that manipulation. All right. The second kind of hallmark of an experimental study or experimental method is control. All right. So control is going to help us to rule out the influence of other variables. So things like participant variables, for example, age, gender, motivation, personality. These are also known as what's called individual differences. All right. So control helps us rule out the influence of those participant variables. It also helps us rule out the influence of environmental variables. So the characteristics of the environment, like the time of day, the weather conditions, and if it's raining, if it's sunny, if it's snowing, things like that. And it's very important to have that control in experimental studies. All right. So we went over what the differences between discrete variables and continuous variables are. We also looked at different scales of measurement for particular variables. And now we're going to look at if we're doing an experimental study, we're going to have two kinds of variables. One is called an independent variable, and the other is called a dependent variable. All right, so the independent variable is the variable that is going to be manipulated by the researcher. All right. So in the example, right, video game, which is going to separate the two groups, that is the independent variable, because that is the variable that the researcher manipulated. All right. The researcher decided which boys are going to go into the violent group and which are going to go into the non-violent video game group. All right. So that's an independent variable. It's independent because no other variable in the study influences its value. All right. Then we also have what's called the dependent variable. And the dependent variable is the one It's going to be observed or measured to assess the effect of the treatment. So it's going to be dependent because it's going to depend on the independent variable. So let's go back to our example again. So the type of video game is the independent variable, but what we're scoring is the second variable, which is the aggressive behavior. So aggressive behavior is the dependent variable because the aggressive behavior depends on the group that the children are in, the type of video game that they played, all right? Either violent or non-violent. All right. So when we're talking about control, so some more about that, which is a very important hallmark of the experimental method, all right? The methods of control, we're going to go briefly through this, right? What we want to do is randomly assign subjects to groups, all right? We want to make it, we don't want to choose who goes into a group. We want to have a process that assigns people to groups based off of chance. So we're going to randomly assign them to groups. Another kind of control is what's called matching of subjects. We want to make sure sometimes that if we have a certain kind of variable of interest, let's say IQ, we want to match participants in different groups on that particular variable. So we want to make sure that each participant has a certain level of that particular variable present. So if the variable of interest is IQ scores, I want to make sure everybody in the study has an IQ score between 100 and 130. All right. And so that when I compare groups, I'm comparing groups of people who have similar IQ scores. All right. So that doesn't become some kind of individual difference that messes up my research results. All right. And then we could hold the level of potentially influential variables constant, right? If I think some kind of variable is very important, that if it's not held constant, all right, then it'll mess up my study, then I'll make it so that I hold it constant. So if I'm measuring depression in individuals, I want to make sure that the way I am talking to the people in the different groups in my study is exactly the same. Because if I end up talking to one participant or one group of participants differently than another group of participants, then when I get my research results, I don't know what is the cause on why I got my research results. It could be because of how my study was conducted, or it could be because of how I talked to my participants. All right. So we want to hold some level of potentially influential variables constant. Usually in experimental method, we have what's called a controlled condition. All right. And in this control condition, individuals do not receive the experimental treatment. All right. They either receive no treatment or they receive a neutral treatment called a placebo. All right. And so the purpose of the control condition is going to be to provide a baseline, a starting point for comparing with the experimental condition, right? So we're trying to see, hey, if we don't give, if we're trying to see if a medication works, we'll have two or maybe even three groups. We'll have one group who doesn't get the medication. We'll have another group who does get the medication. That's called the experimental condition. The one who doesn't get the experimental medication is in the control condition. Then we'll also have what's called a no treatment placebo group, or just a placebo group, and they're going to get a placebo, which is which is going to be some kind of treatment that that the participants think is an actual treatment, but it is not. All right. And so this is gonna help tell us, the researcher, right, how people who don't get a treatment um, are in comparison to those who do get a treatment, or who don't, or to those who think that they received a treatment in the study. All these are very important. And again, the experimental condition are individuals who do receive the experimental treatment. All right. So we also have, that was an experimental group. We also have what is called non-experimental methods. All right. And these are non-equivalent groups. We won't get into too much detail with them, but in these ones, the researcher is going to compare groups, right? However, the primary difference between these and between the non-experimental and experimental methods is that in the non-equivalent groups, the researcher cannot control who goes into which group. All right. So another kind of non-experimental method is what's called a pre-test, post-test, where individuals are measured at 2 points in time. And in this one too, the researcher cannot control or influence the passage of time. All right. And when we're doing non-experimental methods, all right, the independent variable, because it's not truly independent, we call it a quasi-independent variable. Quasi meaning sort of, kind of. All right. So let's look at some examples of this. So in a non-experimental study, right, we have, in this one, we have a group that's separated by gender. Now, I can't control the gender of my participants. They come to the study with their gender already, or they come to the study with their race, or they come to the study already with their IQ level, or they come to the study with their eye color or hair color, or whatever kind of individual difference. I don't control for that. And if my groups are comparing people on that particular kind of individual difference, be it gender or race or ethnicity, then what I have is a non-experimental study where once somebody comes to the group, I put them into the category that they already belong in. So I put all the boys in my study into the boy group. I put the girls in my study into the girl group. And so that would be a quasi-independent variable, right? Because it's not manipulated. I don't manipulate gender or race or ethnicity or eye color, but that particular variable is going to be used to create the different groups of participants. And so variable 2 is going to be essentially the same. The variable number 2 is going to be the dependent variable. And so in this kind of example, I'm going to be comparing verbal test scores, right? So there's a boy group, there's a girl group, and I give them some kind of test, and then I measure their verbal test scores to see if there's any kind of difference between the boy group and the girl group. All right. So that's one example of a non-experimental study. Then we have what's essentially a pre-test, post-test non-experimental study. So I can't control the passage of time, right? So I can't make a group after they had the therapy, right? So the quasi-independent variable is time, all right? Because time isn't manipulated, but it's going to be used to create 2 groups of scores. The group who how they were before the therapy, and then the group how they are after the therapy. And so the therapy, which separates the groups, is the quasi-independent variable. And I'm going to measure or observe the dependent variable. In this case, the depression score. So I'm going to give them some kind of assessment and measure how much depression they have, either how much they had before the therapy, and then how much they had after the therapy. And then I'm going to compare those two groups and see if there's any kind of difference. Okay. So lesson check, learning check 3. All right. So researchers observed that students' exam scores were higher the more sleep they had the night before. This study is what? All right. So is it descriptive? Are we just describing a variable? No, right? There's two variables, and one is, we're saying one is has a score that's higher the more sleep that they had. So it's not descriptive. Descriptive would just be, hey, this is how many times, it's how much sleep that you have on a daily basis, and these are the exam scores that you have in the study that we are conducting. So it's not descriptive, and then it's not experimental, right? We're not comparing the groups. We just said that, hey, one scores were higher for the based off sleep amount. Nor is it non-experimental, right? Because we're not describing two different groups. We didn't talk about anything about any kind of group in this example. So the answer is going to be D. It's correlational, right? We have two variables, and we're looking to see what the relationship is between the two variables. In this case, students' exam scores are going to be higher the more sleep they had the previous night. All right. So decide if each of the following statements is true or false. All right. So true or false, all research methods have the independent variable. Well, that's going to be false. Correlational methods do not need an independent variable. So we're going to learn what the variables are called for those particular kind of studies once we get to correlation a couple of weeks from now. So that's false. Second question, all research methods can show cause and effect relationships. Well, that too is false, right? Only an experimental study can show cause and effect relationships. A correlational study cannot do it. A descriptive study cannot do it, nor can a non-experimental study do it. All right, only a experimental study can do it. And so here are the answers. All right. So now we're going to get into some applied math. Basically, this chapter was more kind of setting the tone and getting some of these definitions out the way so that we can get into the nitty-gritty of statistics. All right. So statistical notation. So statistics are going to use operations and notation that you have already learned. Like I said earlier in the lecture, all right, none of these is beyond the math that you're going to be doing. None of these are beyond the 9th grade, all right? And I highly recommend going again and reviewing the mathematical review in the Appendix A and looking at the PowerPoint slides that I created in the modules, all right? So when we're doing statistics, right, we're going to use specific notation. And the specific notation is going to direct us to what is going on, all right? So when we're talking about scores, so I told you, datum, scores, raw scores, all right? They're either going to be referred to as X, right, if it's only one variable that we're looking at, and possibly Y if we're looking at two variables, all right? The scores are going to be referred to as X and Y. If it's a capitalized, italicized N, all right, that is going to be the number of scores in a population. So we measured something about a total population. right? And a capital italicized N represents the number of scores in that particular population. If it is an italicized lowercase n, right, that's going to be the number of scores in a sample, also known as just the sample size. It's very important. We're going to say sample size a lot in this class, and we're going to deal a lot mostly with samples. So the lowercase n is going to become very important. All of these statistical notations I'm going through now, we're going to be using in every single formula. So it's definitely, you need to understand and make sure you are comfortable with this notation. All right. So a special new thing that you probably did not learn in high school is what is called the summation notation. All right. So many statistical procedures involve summing or adding up a set of scores. Right. The summation sign, known as sigma, all right, that E, like the sigmas, like the fraternity, all right. Sigma stands for summation. All right. And so the sigma or the summation sign is going to be followed by a symbol or equation that defines what is to be summed, what is to be added up. All right. Now the summation is going to be done after operations in parentheses, after squaring, and after multiplication and division. However, summation is done before we do the addition and subtraction. So if it sounds familiar, it's because it is. You've encountered something similar to this. It's called PEMDAS, all right? This the acronym for how to solve the order of solving certain kinds of problems, right? So PEMDAS, the P stands for parentheses, E stands for exponents, M stands for multiplication, D stands for division, A stands for addition, and S stands for subtraction, is now going to be PEMDAS, where we do the parentheses, exponents, multiplication, and division, again, going from left to right, all right? And then once we do the first four, if there's a summation sign, we're going to do the summation. And then after we do the summation, we're going to do any addition and subtraction. So any calculations contained with the parentheses, again, are going to be done first. Then squaring or raising to other exponents, right, is done second. Then the multiplication and division is done third. Again, it's done, a series of multiplication and division operations are going to be done from left to right. All right. And then we're going to do, again, like I said earlier, we're doing the summation using the sigma notation. That's going to be done next. And then finally, we're going to, any other addition or subtraction is going to be done. So the way this looks, all right, if we have the following set of scores, right? So we have 10, 6, 7, and 4, right? The population of scores is 4, right? Because we have this capital N and 4, right? So this represents a total population of scores, 10, 6, 7, and 4. This question is asking, hey, I want you to sum the scores designated by X, right? So I want you to add up all the scores. Well, then you just add up 10 plus 6 plus 7 plus 4, and that's going to give you 27. All right. We're going to do some more problems with this because it can get a little bit more, it can get a lot more complicated, but not something that is actually difficult. Just takes practice. All right. So let's say we have, let's say the scores we have are 3, 1, 7, and 4, right? If I have a sigma, a summation symbol, and X, that means, hey, we're going to sum up all of the scores, the 3, the 1, the 7, and the 4. So if we add 3, 1, 7, and 4, we get 15. All right, but let's say we made it a little bit more complicated, all right? Let's say we have x squared sigma, right? That's how you should read it, because what this is saying is that if we're following PEMDAS, right, the first thing we're doing is we're going to take each score and square it. So we're taking the same scores of 3, 1, 7, and 4, right? So 3 squared, right? 1 squared, 7 squared, and 4 squared. Once we get the squared amounts for those, the next operation says that we are going to sum those scores up. We're going to add those scores up. So 3 squared plus 1 squared plus 7 squared plus 4 squared gives us 75. Now let's say we have the same symbols, but now we add parentheses. Well, because of PEMDAS, that's going to change how we solve this problem. All right. So this one is saying, hey, we're going to take all these scores, right? And we're going to add all those scores together, right? Because the parentheses come first. Once we have that value, we are going to square it, right? So 3 plus 1 plus 7 and 4 gives us 15. 15 squared gives us 225. All right. So now it can get a little bit more complicated, but it's still, if you just work it through, all right, it's very simple. So let's say we wanted to solve this equation, right? This is saying, based on PEMDAS, it's saying that, hey, we're going to take each score and we're going to subtract 1 from it, and we're going to get a value. Once we get all those values for each of those scores, we are going to add those up. All right. And this one is just saying, hey, we're going to subtract 1 from each score that we have. Once we get a value for that, we're going to square it, right? Because we do parentheses first, then we do exponents. All right. So we're going to subtract 1 from each score, then we're going to square it. And then once we do that, we're going to have a value, and we're going to add those values up. We're going to sum those up. All right. And most of the time when we do this, and I highly suggest that when you're doing your homework or when you're doing any of the quizzes, is to make what's called a table. I'm going to go more into a table in chapter 2. All right. But if we do a table, it makes this process a lot easier. So this is the scores, 3, 1, 7, and 4, right? And this is the score minus 1, right? So 3 minus 1 is 2, 1 minus 1 is 0, 7 minus 1 is 6, 4 minus 1 is 3. If we wanted to then square that, it would be 2 squared, which is 4, 0 squared, which is 0, 6 squared, which is 36, and 3 squared, which is 9. All right. Let's say we have different scores. Let's say our scores. I'm sorry. If we sum these up, let's say we summed up 2, 0, 6, and 3, right? We get 11. If we sum this one up, it would be 4, 0, 36, and 9, which gives us 49. All right. All right. So we could also do this when it comes to multiplication. Like I said earlier, right? We could have X variables and Y variable as far as notation, right? They both correspond to usually a different variable, right? So in this one, we have 4 people, right? And here are their scores on the X variable, and here are their scores on the Y variable, and here are their scores multiplied with the 2 variables. If in this one we just wanted the sum of the scores, some of the X scores to be specific, we would just add up 3, 1, 7, and 4. That gives us 15. If it said sigma Y, well, we just want the sum of the Y scores, which is 5, 3, 4, and 2, which would give us 14. All right. So then we have um, then we have uh, um, this one is saying, hey, let's take, if we're following PEMDAS, right? Let's take the sum of the scores of the X scores and multiply by the sum of the Y scores. All right, how do I know that this is what it's asking us, right? So are there any parentheses? No. So there's no P. Are there any exponents? No, right? So so then we would just, is there any multiplication and division? Well, yes, there is, but not until we have summed up the X scores and summed up the Y scores. All right. So we sum the X scores, we sum the Y scores, and then we are going to multiply those two. And that's going to give us 210. And lastly, if I have, this one is saying, hey, what we're going to do first is we're going to multiply, right? We're going to multiply each X score for each person by their Y score, right? And then once we get the scores for the multiplication of the two variables, then we're going to add them all up. So that's 15 plus 3 plus 28 plus 8, which gives us 54. All right. So that is how you would do the summation notation. So there's some practice problems at the bottom. And so we're going to work on these in real time so you get a good flavor of what is going on. All right. So the numbers are 5, 2, 4, 2. Right. Those are the scores, 5, 2, 4, 2. So let's remember that. All right. We're going to put this in here. I'm just going to make sure that you can see this. Let's see. Let's make sure you can see this. Okay. So the scores, so I made this little table and you could use this. This is going to be in your modules as well. The scores are 5, 2, 4, and 2, right? And so the first question is asking us, hey, it's asking us to sum, right, the scores, the squared scores, right? It's because the first thing we're doing in PEMDAS is parentheses. There's no parentheses, right? So the next thing we're doing is going to be exponents, or there are an exponent. It's saying raise each score to the second power, right? Or square it, right? So 5 squared is going to be 25. 2 squared is going to be 4. 16 squared is going to be, 4 squared is going to be 16. And 2 squared is going to be 4. Lastly, if we're trying to solve this equation, right, we're going to take those squared scores and we're going to add them up because we have this sigma right here. So 25 plus 4 plus 16 plus 4 is going to give us 49, right? It's going to give us 49. That's the answer for the first question. All right. So now using those same scores for the X variable, right? We have 5, 2, 5, 2, 4, and 2. And for this one, right, this is saying, this question is saying, hey, solve for this equation. And so if we use PEMDAS, right, remember we're always going to use PEMDAS, right? The first thing is parentheses. So in the parentheses is the score plus 1, right? So that means we're going to take each score on the X variable and add 1 to it. So let's do that, right? 5 plus 1 gives us 6. 2 plus 1 gives us 3. 4 plus 1 gives us 5. And 2 plus 1 gives us 3. And then lastly on this, it says, hey, once you get what was in the parentheses as a value, you're going to sum all of those up. So we're going to add all of these values up now. 6 plus 3 plus 5 plus 3 is going to give us 17. All right, and that's the answer for this one. All right. And so our last one is going to be this equation, right? And this one is saying, hey, if we're following PEMDAS, first we're going to take each score and add 1 to each score. Once we do that and have a value for each of those scores, we are going to square that value. All right, and once we have the squared values of what's in the parentheses, we are then going to add all of those up. All right, so if we're starting this one, well, we have the value of the scores plus 1. And so if we square those scores, right, it would be 6 squared gives us 36. 3 squared gives us 9. 5 squared gives us 25. And 3 squared gives us 9. All right. And so the next part of this is saying, hey, we have to add all those up, right? Because it has that sigma. So 36 plus 9 plus 25 plus 9, all right, is going to give us 79. All right. So that is the answers to the questions that we have right here. Oh, I'm sorry. Oh, yeah, okay. Yeah, different ones. Okay. Okay. Let's see. Some kind of problem done somewhere. 49, 17. Okay, yes. 49, 17, and 79. All right, let's see. Do I have it? 49, 17. Yeah. So here are the answers to that one. 49, 17, and 79. Okay. Okay. So the next question is going to be instructing us on what to do, right? So this says, right, if we just read it, right, if we're using PEMDAS, right, well, first we're looking for exponents, or well, first we're looking for parentheses. There's no parentheses, right? So now we're going to use exponents. So is there an exponent? Yes. So this is saying, hey, first we're going to square each score, right? All right. And now if we're following PEMDAS, right? We're looking for, after we use exponents, we're looking for multiplication and division. Well, there is no multiplication, there is no division. So then the next thing we're looking for is the summation, the sigma sign, right? And so the sigma sign is saying, hey, we're going to add up all of those squared scores. All right, then once we do that, all we're left with is we're going to add 47 to this particular value. So this would be B, right? We're going to square each score, add up the squared scores, then we're going to add 47 to that sum. All right. And we won't go over that last one. You can look at that for yourself. And so that brings us to the end of chapter 1. Now you have all you need in order to be successful in chapter 1. If you have any questions, you can always reach me during my office hours or after class. If I don't have another class afterwards, I believe this one is online. So you can always hit me up on Canvas or an email as well. All right. I thank you, and you have a great day. Peace.